Okay, thank you. So, good afternoon. We'll continue where we left off yesterday. We were talking about bone. Bone, not as so much as a tissue, but as a integral and very essential component of the system called the musculoskeletal system. So we are not looking at the muscular part today, we're looking at the skeletal, and we are looking at how the whole system is fitted together. So we looked at different parts of the skeleton, what different types of bones were there, how we classified them, and so on. And today we'll look at the second part. I think we can finish in about half an hour. I'll try. So here we are. We're looking today at development and growth and healing and repair. So, in other words, we are focusing on the liveness of the bone. What you will learn in anatomy is the cadaveric bone, what we have recovered from a dead body which has been completely dissected, buried for 6 months. We recover the bone, clean it up, remove all its biological, that is, its material attachments, and we are only left with the hard mineralized part. But in life, who you will deal with is live patients with live, very dynamic bones inside them. So let's look at the processes which govern the bones when they are in a live state. The most important, of course, to keep anything and anyone alive is blood supply. So the blood supply of a long bone. We already said the long bone has parts called diaphysis, metaphysis, and epiphysis. Yes, and in these, the type of bone arranged there will most likely be cortical bone on the outside rim of the diaphysis and spongy or cancellous bone everywhere else, particularly at the expanded ends, which may be called the proximal end and distal end, or the medial or lateral end, depending on its position, depending on the specific bone we are looking at. Now, no matter where and what bone it is, a long bone will usually have a nutrient foramen somewhere in the center of its shaft. So in this particular diagram, we are seeing there is an artery. They are not colored here, so even the vessels are black, which is designated the nutrient artery. It penetrates through that cortical bone of the outside of the shaft or the diaphysis and makes a channel for itself and gets into the center space and then divides into a myriad of branches which will form very, very, very fine channels into which the finest capillary network will go and keep each and every osteocyte alive. So if you're looking at it in a colored version, this is what it looks like. In the diaphysis, we will see an area where there will be a nutrient foramen, a rather prominent foramen, which we said was one of those Latin and Greek names for a hole, right? An aperture. So through this will go the artery and the accompanying vein. They'll penetrate inside and they will form a huge network which is very parallel. The branches of the arteries are accompanied by the tributaries of the veins, and wherever this one goes, that one goes. So it's not in this diagram, all the arterial thing is shown on the left and the venous is shown on the right, but in actuality they're all mixed up like that. Wherever there is an artery, there will be an accompanying venule or a venous channel, and the branches will go up and down the length of the shaft and continue to form networks, finer and finer and finer networks, which are going in between those mineralized trabeculae in which these osteocytes have already been arranged in osteons. We already looked at that in yesterday's class very sketchily. I will go into that into deep detail when we start general histology. So I'm saving a little time by just telling you the overview here. But please remember, the cells were called osteocytes, and there were another bunch of cells called osteoclasts, which we are not looking at right now. So the artery has gone up to approaching the metaphyseal area, and then suddenly there seems to be a gap or a line where it's not crossing. The branches of this artery are not crossing that line. Why did that happen? Because if you follow it, they're looping back on themselves. They're forming little end-to-end loops with each other, or the arteriolar branching is continuing as a venular branching and recombining and forming the vein, which will come back, which means that particular line seems to have a deficiency or a very weak, poor blood supply, which means in terms of vitality, it will be the least vital part of the bone. This becomes very important tomorrow in the disease process. You will realize that much of disease, the manifestation of it happens because there is insufficient perfusion. Perfusion is the availability of the oxygen from the blood to the tissue. So the arteriolar tree may be visible, may be very rich. It may look as if there is a great, an angiographic picture may show you lovely arteries available there. But what you must remember is in design, in architecture, these metaphyseal areas. You remember we had talked about an item called an epiphyseal plate yesterday. So that is the one where you have this kind of a watershed area where all the branches go and loop back into venules. They don't get into that particular line. Similarly, there will be blood supply from the ends also. You're seeing there are some veins here, and you're seeing a whole bunch of vessels here. So the epiphyses are again very richly supplied. They have no problem, but that is not coming in via the nutrient foramen. Right? The nutrient foramen is essentially supplying the diaphysis and the metaphysis right up to the potential epiphyseal plate line. And the epiphyseal vessels will be several. They'll be much smaller in caliber. They will have the same pattern of arteries and venules running together. Again, they seem to go touch that articular plate of cartilage, which is purple in this diagram, and not penetrate it. This is another difference in the tissues which is extremely vital for you to remember. Cartilage is poorly perfused. It doesn't have any vessels actually. It's a completely different way of keeping it alive. So these bony vessels will not get into cartilaginous tissue. It's right next to it. Physically, it is very proximate, very intimately attached to it. But this one's blood supply will not go and feed that one. We will come to why and how and all that later, but remember this. So the pattern is such. This is only to give you a concept of the patterns which are happening. So we have a diaphyseal supply via the nutrient foramen, and we have an epiphyseal supply via its own sets of vessels. So the nutrient arteries, the main one which is entering the diaphysis, the metaphyseal arteries, there seem to be some which are entering here also, from the sides. So what they do is penetrate the periosteum, and there will be apertures on the outside of a bone. When we start teaching you bones, you'll see there will be a whole bunch of small holes all over the bone, but some parts will be very smooth, and remember we call them facets, and they're the ones which usually participate in joints or articulations with each other or with other important structures. So there will be a metaphysis penetrated by a lot of vessels, and in the epiphysis again there will be a lot of vessels. And periosteal arteries is a whole bunch of small vessels or networks which are available, but they're very, very small in size, and if we have to make a choice, they can be sacrificed. But we are very, very careful with the nutrient arteries, that is the large caliber vessels, and with the main metaphyseal and epiphyseal arteries. For each area, for each region, for each joint, there will be a certain importance of certain vessels. We will emphasize it as we go along. Apart from what you see on the outside, the periosteal vessels are the ones which are supplying the periphery of the whole bone, the diaphysis, metaphysis, and epiphysis. But inside, once this artery has gone inside and branched and become upgoing or downgoing, or rather proximal and distal branchings, in that area, its branches will be called endosteal vessels. There is no in situ emergence of vessels, though there is a lot of bone marrow here. It doesn't come and supply the bone in which it is housed. That's a completely different design of supply for that. What you must remember is those vessels which you see closer to the inside medullary cavity of a long bone are named endosteal vessels, out of which you can see the arterial ones are somewhat small in caliber, and the venous channel is a somewhat singular larger caliber one, which seems to take the blood from the territory of 2 or 3 or 4 arteriolar channels. We'll go into that detail later when we talk about the applied anatomy. You remember this pictorially, and please follow it up, revise it in your atlases. So this is again the same thing. This labeling is better, so I'll repeat it for you. We had the diaphysis, and we had its vessels, the nutrient artery, nutrient vein going through the nutrient foramen. The outside was compact bone, the inside was a hollow space called a medullary cavity. This sheet, which covers the surface, a fibrous sheet which covers the surface of the bone is called the periosteum. So the vessels supplying it are very fine. They're called periosteal artery and periosteal vein. They usually are limited to the periosteum, but they do have connections with the osteal vessels, right, which are branches of the nutrient artery. The metaphyseal arteries are medium caliber. They get into the metaphyseal space and supply the cancellous bone. They're important because there's a lot of bone marrow here. So actually the metaphyseal veins will be taking away the newly born series of blood cells. It's an interesting thing to remember. So like I said, there is an epiphyseal line where this side vessels and that side vessels don't seem to be talking to each other, and it's important in the development of disease, and especially if a break, a trauma, an injury happens at the epiphyseal line, it will be very vulnerable to non-healing because it's not getting a blood supply very well from either side. So very particularly careful about fractures going through epiphyseal line, especially in growing children. So the epiphysis itself, again, cancellous bone is having its own artery and vein, maybe 2, maybe 3, there's several over here. And as you can see, the articular cartilage is not going to be supplied through this route at all. In irregular bones, we talked so far about long bones. So in irregular bones, now this is a picture of a vertebra. I think you already know this. The central part, which is somewhat soft, this is an intervertebral disc. The central part is called a nucleus pulposus, and the surrounding part is a much more fibrous tissue called the annulus fibrosus. But that's not the point here. The point we are trying to say is the vessels which are supplying an irregular bone are running alongside it. So there'll be one on this side and there'll be another on that side. For purposes of diagrammatic representation, we're only showing one side, and we're showing it as if we're showing the branch which is penetrating and going inside. And what's happening inside is, if you opened it out partially, we would see that the arteriolar branching is going almost circumferentially around this cylinder-shaped body of the vertebra and giving downgoing branching vessels which are going towards the lower surface. So for each vertebra, the supplying arteriole seems to be closer to the upper surface, and its branches which are downgoing are going to supply all of it, including the lower surface. And in between there will be a cartilage. This intervertebral disc is a specialized type of cartilage. It will not get supplied through this blood supply. Remember, the bone blood supply and the cartilage blood supply are not from the same vessels, but the cartilage will obviously need to be kept alive through a different way. It will be supplied by separate articular branches of the same parent vessel, but not the ones which we have named already as the nutrient vein and artery, the periosteal vein and arteries, the metaphyseal veins and arteries, the epiphyseal veins and arteries. None of these are going to directly interact with the cartilage on either end of the bone. These are important when a baby bone, a juvenile bone, is being formed. We said there were 2 ways in which it could proceed to get ossified. There is a difference between being calcified and ossified. Calcification is usually a pathologic process, but ossification is a very dynamic metabolism where the nature of the tissue itself is being changed. The whole bunch of living things which were cartilage are destroyed and replaced by a whole bunch of new living things which will form bone. Okay, it's not like you're converting a cartilage by depositing some calcium in it. Completely different. So the ossification, being such a sophisticated developmental process, takes a long time to happen, and that's good because that slowness permits growth, permits remodeling, permits shaping, permits push and pull, and the whole skeleton responds to the dynamics of internally growing organs, largely growing brain, more data coming into the organism from the environment, adapting to whatever living conditions are outside. So the whole skeletal system is a very dynamic response system to whatever load is being put on that animal. The laws of ossification are such that the base tissue, which is going to finally become bone, is essentially a membranous tissue. It could directly get ossified, in which case we call it a membranous or intermembranous ossification, or it could go through a process of chondrification and then the next stage, second stage of ossification. Now, whichever way it may be, when the first beginning of the process starts, we call that a center of ossification, and The first one to appear is called the primary center, and it always appears before birth. Or another way of looking at it, if the center of ossification has already appeared before the birth of the child, then it is a primary center of ossification. Anything which appears after the child is born is called a secondary center of ossification. Where in a bone, bumps and protrusions and crests and ridges and condyles, all kinds of projections are found. Where there is a pressure and a traction epiphysis, the center of ossification which appears in the pressure epiphysis is earlier than that in the traction epiphysis. Now, right now, this may not seem very important to you. So, what difference does it make whether it's earlier or later? But the age at which a center of ossification appears is very important in the aging of a bone. And in a live person, it will be a very important data point for telling the age of your candidate, of your patient, or your, sometimes in cases of a dead body or a accused in a crime, where age becomes very important point on what kind of punishment they'll get if they are going to be convicted of a criminal offense. So in the arena, in the world of jurisprudence, medical legal science, the aging of bones of the entire skeletal system is a super specialization, and much of that depends on how ossification has proceeded, particularly in the long bone. So just remember this third point. If a bone has a pressure and a traction epiphysis, the pressure one will appear earlier and the traction one will appear later. So if you remember which epiphysis is which, to some extent you will be better able to remember their age of appearance of the center. The law of union of epiphysis is important. That epiphyseal center which appears first. Now, if you have a diaphyseal center, usually that's a primary center and it will be in the center of the shaft. The epiphyseal center, the proximal and distal, will appear later. They usually will be secondary in nature. That means they will usually appear after birth. The one which appears, let's say, in the proximal part of the bone, the secondary center appears first. After a few weeks or a few months, or a year, the secondary center of ossification appears in the distal part. So when you x-ray that bone, it will have one bony bit in the middle which has come from the primary center, and one little bit on the top and one little bit on the down, which are bony, which show up in the x-ray. And the one on top or proximally has appeared first, and the one in the bottom has appeared later. Okay, so you're taking serial x-rays of this individual at age, let's say 5, and then at age 8, and then at age 10. And you got one center of ossification, then you got the second, which is proximal, then you got the third, which is distal. But the one which appears first does not fuse first, it fuses last. Which means, let's say the age of appearance is in the proximal is 8 and in the distal is 9. Right? So we will expect the one which appeared first at the age of 8 years to fuse first, maybe at the age of 15 years. Right? But it doesn't. The second one which appeared will fuse first at the age of 15 or 16, and the one which appeared earlier will fuse last at the age of 17 or 18. This is the general rule of thumb which you can more or less apply to all long bones. For specific bones, we will be telling you these ages. You do not have to memorize them, but there are a few which are critical, which are useful in forensic medicine, which you will start next year. We will emphasize those for that specific bone. Just remember the law. The law of union is the center of ossification in the epiphysis, which appears first, fuses last, right? And vice versa. The one which appears last fuses first. Fuses means the secondary center fuses with the primary center. So then the whole bone has to become one piece. So at one age of the bone, it is in 3 pieces. There's a diaphyseal piece and 2 epiphyseal pieces. And usually a little after the puberty of the individual, right? When they enter into sexual maturity is when your bones, centers of ossification, all of them fuse together, and each bone ends up having one total continuity, and then we call it a singular bone. Till then, that single bone, let's say your humerus or femur, will look like three separate bones when you do the x-rays of the growing individual. So this appearance of the center and then the proceeding of the ossification are happening continuously, not only after birth but starting from before birth itself. So we start, if that particular bone is going to undergo the process of endochondral ossification, these are all the stages through which it will go. In this case, let us say we are looking at the femur of a fetus. The femur is the thigh bone. So the first, there will be a cartilaginous template of the femur in the lower limb region of the developing fetus baby, right? At this time, the little baby doesn't even have a full lower limb. It has a little bud jutting out from the torso. It doesn't have any separation into thigh and leg and foot, and just the beginnings of its core structure of that limb are coming out. So it looks, for all practical purposes, it looks like a seal, those flap limbs. But it's going to very rapidly develop, and according to a very sophisticated preset plan, right? So there's going to be a cartilage template, then the central cells are going to hypertrophy or increase in size, then the primary matrix is going to get calcified from that primary ossification center. So till here you're all cartilage. Here ossification has started at some point, and that is the point we are going to call the primary center. And at its periphery there will be a collar of bone which is just under the periosteum. So we call it the periosteal collar of bone. When this tissue change is beginning to happen, when it has already got triggered, is when the surrounding vasculature, the vessels are also developing outside of this model. They will give a branch which will penetrate, which will become the future nutrient foramen, allowing the nutrient artery to come in. And this influx of blood supply, oxygen and nourishment increases the pace of growth very rapidly, and a whole bunch of tissue is burgeoning at a rapid pace. So you have these blood vessels and you have a whole bunch of cell divisions happening, so that osteoblasts are converting into osteocytes at a rapid pace. They're secreting matrix, fibroblasts are secreting fiber, they're all getting arranged in certain formats, and this is like a wave front, like a series of soldiers. They're moving forward in both directions towards the end of that cartilaginous model. So when they do that, the primary bone is laid down on this calcified cartilage remnants, and the secondary center at this time appears in this end, in whichever one of the ends, right, of the bone. So when it appears here, again it pulls a blood supply with it, right? The occurrence of a center of ossification stimulates or triggers changes in the surrounding vasculature to allow a vessel to penetrate into this model and get into the area where great deal of cell division is required. So when a lot of energy is required, you have to have a very good blood supply attending it. So this is happening. It has pulled in one metaphyseal vessel, actually epiphyseal vessel, where the secondary center is started. The continued growth of the cartilage of this epiphyseal plate and epiphysis allows a whole bunch of red bone marrow to also form there. So not only is bone being laid down, which is one type of tissue, but also bone marrow, which is hematogenous tissue, completely different cell line. One will never become the other, but it's all happening in the same place because of the same rich blood supply which is available. And all this, you must remember, is a play out of the genetic code which is happening according to a particular preset times, timing mechanism within the organism. So in our case, the human being. So you have, can you see, this is the epiphyseal vessel, and it is giving branches and branches, and in between there will be a hematogenous tissue preparation also. In the meantime, in this area already solidification is happening, cortical and cancellous bones is happening, which means mineralization is happening. The matrix is being insufflated with calcium hydroxyapatite crystals, which will freeze it into a certain shape, but it is not a permanent frozen shape. Osteoclast cells are available which can remodel the bone at proceeding stages. So when the cartilage growth stops and complete ossification of the epiphyseal plate happens along with the so the diaphysis and epiphysis cannot be differentiated anymore, right? Can you see? Here you can see this was cartilage, this is forming bone, this is still cartilage, this is bone which is fully formed. So when fully formed bone here and fully formed bone here are separated by the cartilaginous area, that area will look like a gap in an X-ray, right? And you will see the bone as separate pieces. But when complete cartilage growth stops, then the whole to all the centers available fuse. That's called the fusion of the epiphysis with the diaphysis, and the red bone marrow will get replaced by yellow adipose bone marrow in most of the adult long bones. So the stages of endochondral ossification have been laid down. You can please note it down because this is also an exam question, or you can revise it again at your leisure. There is a growth stage where there is cell division, where there is interstitial and appositional growth, and the cells are found in columns or palisades. You can see these are cartilage cells, but there will be bone cells also laid down like that. Then the stage of transformation, where the cells increase in size and the matrix, the surrounding tissue, gets calcified. Then the stage of ossification, where the chondrolysis means lysis is breaking down and chondro is cartilage. The original cartilage gets broken down completely. Blood vessels come in, so vascularization happens, and osteogenesis or division or generation of bone tissue via the multiplication of the osteoblasts and formation of osteocytes. And then remodeling as a last stage, the final shape, the shape and features, contours of the bone are laid down by erosion of the extra laid down material and deposition in the particular shape that is required for that bone. So this is another picture saying the same thing. We first have a cartilaginous bundle, then you have the calcified cartilage with the developing periosteum, then you have the compact bone developing in the periphery of the diaphysis, blood vessel penetration, appearance of the primary ossification center. At the same time, or rather at the next step, you have the appearance of a secondary ossification center, again penetration of the blood vessels, and here already the inside of that cartilage, which was solid, is now becoming hollow to make place for the medullary cavity, which must house the hematogenous tissue. And then while this is proceeding in both directions, a epiphyseal disc, at this stage you can call it an epiphyseal disc, in some books they call it a plate, in this case it's spelled D-I-S-K, in some places it will be spelled D-I-S-C, both are right, you're okay with that. But plate is I think a more clinical term that they use. Then you have fusion of the epiphyseal pieces with the whole diaphyseal piece. So at this point you can see the bone is 4 different pieces, right, separated by all these unossified areas. But at some point of maturity, all the pieces will fuse together, and that's when we say the bone is completely ossified and is of its adult parameters, diameter, length, etc., whatever. So on top of the projections, wherever the bone features are participating in a joint, it will be covered with an articular cartilage. The type of bone will be set by now, whether it's compact bone or spongy bone, and the remnants of the epiphyseal discs will slowly start disappearing. Maybe a very fine line will be seen up to a certain age. This I showed you yesterday, right? A baby's arm, to show you that our radius and ulna here don't seem to have any ends, right? The humerus also doesn't seem to have any ends. But if you look at it, they will appear. This is a very small baby, and this whole piece has grown from the primary center of ossification. The baby is already born. Neonate means it's already born. As the baby grows, a center will appear, one little dot of white will appear, which will be the epiphyseal secondary centers for that particular long bone. And then the baby will grow some more, become a child, become a walking, talking preteen, and then once they become teenagers and attain mature puberty, then these secondary centers and primary centers will fuse together, and the length of the long bone will be set once that fusion happens. So that whole process, which was there diagrammatically, it's actually here, it's an actual section where you see ossification proceeding here. This is the cartilaginous ends, which haven't yet started. In these bones, these are the tarsals, ossification hasn't even started. It hasn't even started undergoing that 5-stage process. This is a histological picture, same thing, but stained and magnified. blown it up a little bit more, so you're seeing the finer cellular architecture and you're seeing the blood supply. You're not seeing the vessel which has gone in. Actually, this would be the periosteum. This, if you're seeing the periosteum very, very sharply, then there must be a particular stain for fibrous tissue, because periosteum is essentially fiber. So we will go into what stains we use to highlight which tissue when we do histology. Bone, calcified bone cannot be stained because that hardened mineral cannot take any color which you put on it, cannot take any dye. So we study bone as what we call ground sections. We grind it into a very, 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 very thin slice, and then we look at it under the microscope. We can't do anything else with it. So it's a black and white or brown black and white picture, but you get a very nice look at the arrangement of the osteons, right? So in endochondral ossification, there was a cartilage template, there was hypertrophy, then there was calcification in the primary ossification center, formation of periosteal collar. Then D, there was invasion by vascular osteogenic buds. E, there was a primary bone laid down on the calcified cartilage remnants. Then the secondary center of ossification appears and becomes vascularized. Usually, by the time D is done, before E, the child is born. Alright? But sometimes you can have an epiphyseal center occurring even before birth. Actually, I don't think there is an exception to the rule. If there is, you people must point it out to me by paying attention in the class. Okay? There's continued growth of cartilage of the epiphyseal plate and epiphysis, and proliferation of the red bone marrow. And this is just a recap of what I've already told you before in a bigger font, so if you want to take notes, this is a good time. But I think this lecture is available for you to revise, so you can do that at leisure. You don't have to get stressed about it right now, right? You access it a little later and you can note down these points, or just go to a standard book, standard general anatomy book. All of this will be there, right? Some of you enjoy taking notes. You are trained to take notes in your intermediate, and some of you hate taking notes. So whatever works for you, you do it, but make sure you don't waste too much of time, because writing down notes is not the end point of your medical education, right? It has to get into your brain, and it has to be permanently etched there, because it has to be recalled at any point that you need it without reference to a book. So whatever it takes to help you anchor this in your memory, you do it, right? Slowly, it will take you 2 3 months to figure out what's the best way to study, what's the best way to retain. You do whatever works for you. Some solo study, combined study, group study, but study at the end of the day, right? At some point, somehow, please study. Cessation of cartilage growth means stopping. So only when cartilage growth completely stops and ossification completely finishes, then you'll have a fusion of the epiphysis, and there won't be any remaining epiphyseal plate. There is nothing here which even shows that at some one point of time there were 3 centers of ossification and there was a line across which the blood vessels were not running, and all of that. All that whole phenomena is finished when the 3 centers fuse with each other, and at the same time the bone marrow also transforms. The second type of ossification is called intramembranous ossification. Right? This is a very interesting picture because it's an actual photomicrograph. That means we took a piece of bone which was in developmental stage. That means it wasn't yet bone, it was a membrane. And since it wasn't mineralized, we could stain it, right? So we took a very thin slice, we cut it with an instrument called a microtome into some 7 to 8 micron sections. Then we put it through a process of dehydration, rehydration, all kinds of stuff. Then we added a pair of stains to it called hematoxylin and eosin. Eosin stains reddish, pinkish, and hematoxylin stains purplish, violet shades. So all of histology will be in shades of pink and violet, and your discerning eye will have to make out all the very fine architectural detail through that. So what you see is there is a whole bunch of mesenchyme. I'll introduce these terms later, but there's a whole bunch of mesenchymal tissue in which bones, trabeculae, are being laid out, right? Those strips, what look like bars of bone to the naked eye, are looking like purple bands over here, and inside of them you're seeing these little hole-like things, purple dots surrounded by white space, purple dots surrounded by white space, right? So that is a osteocyte inside its space or lacuna. and in between them is a lot of empty looking space filled with blood vessels, and these are all RBCs within a vessel, RBCs filling up a vessel section, and so on and so forth. So basically what you're trying to say is, first there was membrane and then there was bone, so where's the cartilage? It didn't happen. This process is called intramembranous ossification. So the membrane model did not have to undergo an intermediate step. Straight away the osteogenic material or osteogenic cells penetrated and began a center of ossification, or rather the local cells de-differentiated into osteoblasts and started their job. Right? They started laying down matrix, laying down fibers, making lacunae around themselves, and converted it into bone. This is all when growth is happening, right? Through the long years which it takes for us to change from a child to an adult. But along that time, sometimes there may be a requirement, because of certain activities you do with your bones, or certain pressures or certain pulls which are put on the bones, that more weight or more traction is applied to one part of the bone, and then the original cartilaginous model, which has now been replaced, is being replaced by bone, will respond to that dynamic pull or push, and the shape which was originally set can be changed in response to the environmental pull. You must remember this. I cannot emphasize it enough, that bone is a highly dynamic situation. It's not a thing, right? It's a live, responsive, metabolic situation, always responding to what is required of it. You put more weight on it, it'll grow a certain way. You put less weight on it, you're sick for 6 months and you're on the bed. All your bones, your entire skeletal system will respond to that lack of exercise. Alright, its shapes, its weight, its ossification will change in response to that. Right? So the remodeling of a long bone happens because the original model is of a certain shape. Then the juvenile model is almost the same but slightly different shape, and then the adult model on that will be of a different shape. So you see, this bit will have to be absorbed so that it will become narrow and thinner, and this bit will have to grow and expand, right, and have become much wider than this or this dimensions. So this whole process of changing its shape and its dimensions in response to a growth phenomenon or a response to environment phenomenon is called remodeling. It has to include some areas which will be absorbed and other areas which will grow in length and in shape. How will that happen? So when a ring requirement is there, some part will have to be, we said, absorbed. So at some point you have this new bunch of cells called osteoclasts. They're not the same as the ones which were laying down the original bone, right? They go and they literally eat away the bone that is already available over there, right? So this whole bunch of osteoclasts are dissolving the bone material that they are coming into contact with. They are acting like phagocytes. They are actually in their vicinity. Then inside the center of that empty, now it is formless material, right? There's no cells or fibers or lamellae or osteon, nothing. It's all been reduced to just a will develop, and these fibroblasts, mother cells, which can decide to become fibrocytes, or they can decide to become some other kind of cell. At that point, these fibroblasts will start laying down the fibers in the new pattern that is required of the bone, right? We've already eaten away the old pattern. Now there is a scope to lay down a new pattern, and that area is therefore called the reversal zone. So where the osteoclasts are proceeding forward and removing material is called the cutting cone. The area just behind it where the new fibroblast activity has started is called the reversal zone, and the core of it is always occupied by a blood vessel, because without energy nothing will happen. right? The blood will bring in the oxygen and the new material and the glucose to keep everybody fit and active, right? These lining cells have not yet decided what they're going to be, right? They are osteoblasts. They can potentially become osteocytes, and they can still divide in huge numbers, because you will have to lay down more matrix once we decide what shape we want, right? This area becomes narrower and narrower as you observe the what shall we call it, time elapsed from the time that resorption started, remodeling started, to the time that it completely completes. So we will see that there will be a osteon formation slowly, because in this area the osteoclasts are moved out and away, and the osteoblasts will move in, and they will start laying down again concentric lamellae of mineralized matrix. In between, they will get trapped because they're laying the lamella all around themselves in all that 360 degrees. So they can't move anymore because their entire environment is mineralized. But they are kept alive by the formation or the leaving behind of these canaliculi, in which fine blood vessels of this parent artery will have penetrated. So at the end of it, in the center of the osteon, is the blood vessel. There is no other cells left, but the in most intimate layer around the vessel is still a small population of osteoblasts, which can jump into action if ever called upon. So they're always there, they're always alive, and they're capable of very rapid multiplication or mitosis, right? So this area of that activity is called the closing cone, because layers are being laid down and the space available for the osteoblast and for the vessel is closing in. It's becoming narrower and narrower and narrower. At this point, sometime the osteoblasts decide to go into a quiet mode and will not divide anymore, and you have the new osteon already laid down here. So this is a timeline. So the oldest part of this whole bone remodeling activity will look like this in cross section. This has happened before. This is following later. This is following later, and this is the newest thing which is happening, is this osteoclastic activity, right? So the names of those zones are as per this diagram. So we looked at a lot of stuff today, a lot of new terminology, but I think the concepts are not so hard. But we've broken down each process into its very small bits, component bits, and that's important for you to know right now. And you will actually see it in action when your patients come. At that time, you can't cut them open and see all this happening, right? But you must remember that that's what is happening inside, and the medicine you prescribe and the bandage you tie and the investigation you order and the surgery you plan, all of that will depend on what you can predict is happening inside your patient's body. So for that, you need to know the processes of repair and healing. The basic scientific processes are those of bone ossification and bone remodeling, isn't it? Those are the two things that we saw. We said there is a endochondral and intramembranous ossification, and we said there is a thing called remodeling of long bone, of any bone for that matter, and that is always in response to a new need. Originally, it will only follow your blueprint of your genetic blueprint. This bone should be this long, this heavy, this big by the time this human being is attained his full height. So that blueprint in a pygmy of the Congo region will be very different from an Eskimo of the Arctic region, because their genetics will be varying from each other in those genes or in those gene groups. But the local situation for that individual human being, no matter which geography, which race, which part of the world it's happening, or which group of people it is happening in, the basic scientific processes that we know of are ossification and bone remodeling. But